do you send a rainbow that broke the law? To prison. Welcome back to Astronomy 101, taught by me, Skylar, an astrophysics PhD student. This is a course designed to kind of be like an intro astronomy course in college. We're going to cover kind of all of the main broad categories of astronomy and astrophysics. We talked last week about what is out there, all of the things that make up the universe. And this week, we're going to talk about how we actually observe them. The primary tool used by astronomers is light. That is how we as humans see, and so that is how we see the universe. Now, there's a lot of different things that go into this, but let's just talk at first about what light is. Something you may know about light is that it's kind of weird, because it acts like both a wave and a particle. So how does that work? Essentially, this means depending on what you want to do with it, you can treat light as a wave or as a particle. As a wave, you can imagine a light as just a little squiggle, and these wavefronts move through the universe. We know that light is a wave because of something called the double slit experiment. What the double slit experiment did was it took a laser and then it pointed it through some sort of material that had two lines cut in it. Now, if light were particles and you were sending individual particles through two gaps, you would expect on the other side to just see two lines of light coming at you. But that's not what they saw. They saw this instead. Now, what is this? This is an interference pattern. This is something that happens when you have a material that is a wave. If you were to do this with water, you would have two waves coming out of the two slits, and there will be points where those waves interact. Now, you can have interactions where you have the peak of one wave and the bottom of the other wave, and they cancel out and make the water flat. When we're talking about light, this is the equivalent of making it look dark. And then you'll have regions where they get amplified. The peak of one meets the peak of another, and they go up. This sort of behavior, where instead of seeing two lines and instead seeing this multiple line interference pattern, proved that light has to act like a wave. But here's the thing, light also has to act like a particle. We can think of shooting a single light packet at something. We call this light packet a photon. Photons are massless, and so they're kind of hard to visualize. You can't think of like a little sphere because it doesn't have any mass. But we can talk about individual particles of light called photons. When we talk about light, there are three main important equations. And I'm trying to keep this course kind of math light, but these equations are important, so we're going to talk about them. These equations relate some of the crucial concepts about light, things like the wavelength, the speed, the energy, and the frequency. The first equation talks about the speed of a light wave. Now, the speed of light we often denote with c. c is the speed of light in a vacuum, and it is 3 × 10⁸ meters per second. That's an important number. Now, the speed of a light wave is just equal to the frequency of that light wave times its wavelength. Now, what do those mean? If we are to draw a wave, it looks something like this. The wavelength is simply the distance between two peaks. We denote it with a lambda, which is a Greek letter that looks like an upside down Y. That's wavelength. Frequency tells you about how often, how frequent you see these peaks passing by you. If you were to imagine standing here and let this wave travel in this direction, the frequency tells you how many peaks pass by in the span of 1 second. So if we think about units in this equation, you have frequency, which tells you how many peaks pass by in 1 second. So it's something unitless over seconds. And then wavelength, you can measure in units of distance, something like meters. So you can see that what you end up with is something that has units of meters per second, like a speed. Another important equation tells us about the energy of a light wave. The energy is equal to h times the frequency. H is Planck's constant. Just Google it, that's what I do. We can think about combining these two equations and rearranging this top one and substituting it into the second one to get this. E is equal to h times c divided by wavelength. Because if we were to rearrange this equation, frequency is just the speed divided by the wavelength. These equations are really important when we talk about converting between light as a particle and light as a wave, because it's really easy to think about the frequency or the wavelength of a wave, but when we talk about a particle, it's much more interesting to think about its energy. And so these equations tell us how you can convert between ideas like waves and concepts like particles. Now, something that's important to note about light is that it comes in a large range of wavelengths. We call the entire range of wavelengths that light can come in the electromagnetic spectrum. The electromagnetic spectrum is shown here, and as you can see, the wavelengths of light range from fractions of a fraction of a fraction of a meter out to hundreds of kilometers. It comes in all sorts of sizes. The crucial thing here is that light will always travel at the same speed, and so when you have long wavelengths on one end of the spectrum, like the radio waves, that always corresponds to short frequencies. And at the other end of the spectrum, where you have short wavelengths, that corresponds to high frequencies and also high energies. So light that is in the form of gamma rays is going to be much more energetic than light that is in the form of microwaves. The light that we can detect with our eyes is called the visible portion of the electromagnetic spectrum. It ranges from about 400 to 700 nanometers in wavelength, which is a really tiny portion of this spectrum. Our eyes can only detect a fraction of a percentage of all the light that is out there in the universe. So one of the important things that astronomers can do is build telescopes that look not only at visible light, but at light in all of the different ranges of this spectrum. And we'll talk more about some of those telescopes later on. So that's light, but now let's talk about how astronomers use it. And one of the important things that astronomers look at are called spectras, which are just the result of blocking out light into all of its separate wavelengths. A great example of this is a prism. If you have ever hung a little crystal in a window and watch it create rainbows around your room, you are creating a spectra. You're taking the white light in from the sun and breaking it up into all of the different colors. And the fact that you can do this with light is so useful for astronomy. The science of taking in light and breaking it up into its individual wavelengths is called spectroscopy. There are three main types of spectra that we see with spectroscopy. The first is a continuous spectra. This is the sort of thing you would get if you were to take the light from a light bulb and break it up into the wavelengths. It looks smooth. There's no jagged peaks. You're getting a nice, consistent amount of light from each wavelength. Now, if you were to take something like a light bulb, which is hot and dense and emits a continuous spectrum, and then you put a cloud of cool, diffuse gas in front of it, you would get what is called an absorption spectrum, which looks like this. You take that continuous spectra and then you cut holes out of it because that gas is going to absorb light at specific wavelengths, and we'll talk more about that later. Absorption spectra are actually what we see from stars because the hot, dense core of the star acts like the light bulb, and then the cooler, more diffuse atmosphere of the star absorbs specific wavelengths. So if you were to look at the sun, you would get an absorption spectra like this. The third kind of spectra is called an emission spectra, and this comes from a hot but diffuse gas. An emission spectra is kind of like the inverse of an absorption spectra, where you don't get a lot of light at most wavelengths, but then you'll have peaks where you do see light. We see this when we're looking at hot gas in the universe, of which there's a decent amount in regions of like our own Milky Way galaxy. So for absorption and emission spectra, how do we determine what wavelengths we're either going to see those peaks or dips in the light? As it turns out, it has to do with the structure of an atom. So let's do a little bit of review about that. Atoms are made of three main particles: protons, neutrons, and electrons. The protons and neutrons are clumped together in what we call the nucleus of the atom. The electrons are around this nucleus. Now, there's a lot of different ways to draw this, and chemists, don't get mad at me because I'm going to do it in a somewhat not physically accurate way. Something that's important to note is that electrons aren't just found in random places around the atom. You wouldn't just find an electron floating at some arbitrary distance. Due to the highly annoying branch of science that we call quantum mechanics, electrons are actually only found at very discrete specific locations. We can call those locations energy levels. You can think about drawing a circle around a nucleus and these concentric circles form the different energy levels that an electron can be at. So you could have an electron here, but you couldn't have one here because it's in between energy levels. Let's construct some sort of arbitrary atom. We'll make it a hydrogen atom, which only has one proton, and then let's say this energy level has an energy of 1, this has an energy of 3, and this has an energy of 5. The electron in this atom will most likely be at the lowest energy level. This is kind of a law of nature. Things like to be at low energies. We call this lowest energy level the ground state. So if you were to just have some hydrogen floating around in the universe, it would probably look like this. To be clear, these energies are completely made up. The actual energies of a hydrogen atom look nothing like this. Now what if we put this hydrogen in the way of some light? So let's send in a light wave. This light wave comes into the atom with some set energy. If you remember, the energy is equal to Planck's constant times the frequency, or Planck's constant times the speed divided by the wavelength. So let's just say that this light comes in with an energy of 2. That energy can get absorbed by this electron, and now this electron has not only the energy of 1 from the ground state, but additionally, plus 2 gives us a total energy of 3, which means our electron can now bump up to the second energy level. We call this process absorption. A light wave gets absorbed by the atom, and the electron gets boosted up to a higher energy level. The key thing here, though, is this light has to come in with very specific energies. If this light came in instead with an energy of 1, that would only boost our electron up to an energy of 2, which is not corresponding to a discrete energy level at all, so it would just stay at the ground state. Now, let's imagine that we have our electron having absorbed the energy of the light hanging out at this second energy level. As I mentioned before, electrons don't like being at high energy levels. It's going to want to fall back down. And when it does so, it has to release the extra energy corresponding to being in this ground state. It releases that extra energy in the form of light. So by falling back down, a light wave gets emitted. This will have an energy corresponding to the difference in these energy levels, in this case, 2. This process is called emission because a light wave is getting emitted. The emissions of this light wave will again only happen at very specific energies. You will never have light emitted from this atom that has an energy of 1 because 1 does not correspond to the difference between any of these energy levels. Here's the important thing. If this were a different atom, let's say it was helium, which has 2 protons and a couple of neutrons, these energy levels would be different. You could still have an energy of 1 at this level, but this might correspond to an energy of 2. Now, all of a sudden, light that comes in with an energy equal to 1 can be absorbed by the atom. And so the light that gets absorbed by helium is different than the light that gets absorbed by hydrogen. As it turns out, every single element in the periodic table has very specific wavelengths/energies of light that it will emit or absorb. So you can create a periodic table out of the different colors of light that will get absorbed or emitted by each atom. It looks like this. This is so cool for astronomy because what this means is we can look at the spectra, let's say, of our sun and see at what wavelengths the light is being absorbed and know what elements have to be there. This process right here is how we know what our universe is made up of. It's so cool and it's so important. We can also do a technique called photometry, which, as opposed to looking at each individual wavelength, looks at broader bands of wavelengths. Let's say every wavelength that's the color green, and tells us how much light we get from that. This requires less resolution, so it's a little bit easier to do, and it can tell us things like the general color of an object or some things about its brightness. We can also, of course, take this data and map it out to locations in the sky and create images. We take the total amount of light in some wavelength and some band of wavelengths, and we see what the sky looks like in that color of light. But to do any of this, we have to collect the light. And that is where telescopes come into play. Before I talk about telescopes, I just want to say that the actual optics of telescopes requires a decent bit of complicated math and physics, so I'm not going to get into that too much. We're just going to talk about their general design, the different types of telescopes, and show you some cool pictures of the telescopes that are in use around the world and outside of it right now. There are two main types of telescopes: reflecting telescopes and refracting telescopes. And the key difference in them is whether their primary optical tool is a mirror or a lens. There are very, very few refracting telescopes in use today because the actual engineering of building large lenses is really difficult, and it's much easier to build large telescopes using mirrors. So I'm going to focus on those, but just know there are telescopes that use the lenses. Now, there's a few different designs you can use for reflecting telescopes depending on how much curvature you want the mirrors to have, how you want them to be angled, and stuff like that. What I have behind me is a reflecting telescope, so I'm just going to walk you through the layout of this one. Every reflecting telescope has something called the primary mirror. In the case of this telescope, it's that mirror down in the back, where you can kind of see my phone reflected. The size of your primary mirror tells you the size of the telescope. This is about 5 inches, so we would call this a 5-inch telescope. The primary mirror of JWST is about 6.5 meters across, so pretty big. Now, how this telescope works is light comes in here and gets sent to that primary mirror in the back. That mirror is not perfectly smooth. It is actually a little bit bent, and so it focuses the light into the center instead of sending it right back out. That light then hits the secondary mirror, which is what is attached to this little bit here. The secondary mirror is also a little bit curved, so it will further focus the light. It's also at an angle, which you can kind of see, and that angle shoots it up to the eyepiece. The eyepiece has some complicated system of lenses, and this is what you actually look through when you're looking through a telescope. That's pretty much it when it comes to the basic design of a lot of telescopes, but let's talk a little bit about the things that they do and the mathematical properties of them. Now, one of the primary roles of a telescope is to collect light. And so one of the things we can use to describe its capabilities is its light gathering power, which just corresponds to the size of the primary mirror. The bigger that primary mirror is, the better you can gather light. That's a big reason why we try to make our telescopes as big as possible. Another reason you want to make your telescopes as big as possible is for something called resolution. Resolution tells you how well your telescope can resolve. If you have two objects that are really close together, can the telescope tell that they're actually two objects, or would they look like they're just one object within the capabilities of the telescope? Now, the resolving power of the telescope depends on two things: the diameter of the telescope's primary mirror and the wavelength of light that you are observing. This is the equation for the resolving power of a telescope, and you can see that the longer you make your wavelength, the worse the resolving power gets for a fixed diameter telescope. This is why when we want to look at the long wavelengths in the electromagnetic spectrum, we like to use bigger telescopes. It's one of the reasons that JWST, which looks in the infrared, is larger than Hubble, which looks in the visible primarily. One other important feature of telescopes is that they magnify what you're seeing. And the amount of magnification you get depends on the focal length of your primary mirror and your eyepiece. Focal length essentially has to do with the fact that these optical systems are curved. So if you send light in here in parallel beams, when they hit this mirror, they're not going to get sent straight back. They're going to get bent inwards, as I had mentioned. We're going to pretend this actually went to the mirror. The focal length is the distance from the mirror to where the light focuses. In an eyepiece, it's something similar. In that case, you have a lens, and the light coming through the eyepiece when it enters the lens gets bent inward to the center, and to the point where they reach is the focal length. The magnification of a telescope is just the focal length of the primary mirror divided by the focal length of the eyepiece. So the smaller the focal length of the eyepiece, the higher the magnification. The larger the focal length of the primary mirror, the higher the magnification. So with this understood, let's talk about some of the most important telescopes that are in use right now. I've already done a whole video on JWST, which you can check out. I'll link it somewhere. JWST is a space telescope, meaning it is outside of Earth's atmosphere, and it looks primarily in the infrared. It's the next generation of Hubble, which is another space telescope that look primarily in the visible. There's some other space telescopes as well, like Chandra and Spitzer. Chandra is an X-ray telescope, which can look at very high energy events in the universe. Spitzer looks at longer wavelengths out in the infrared. Space telescopes are super useful because the atmosphere causes all sorts of problems for astronomy. It distorts the images, the atmosphere is itself emitting in certain wavelengths of light, you have to worry about weather and humidity, it's a whole mess. So we like to put our telescopes up in space, but that's really expensive. So a vast majority of our telescopes are ground-based. The Keck telescopes are a very well-known pair of telescopes on the top of Mauna Kea in Hawaii. They can look in both the visible and near-infrared, so wavelengths that are just slightly longer than we can see with our human eye. Another cool telescope is called ALMA, which is the Atacama Large Millimeter Array. It's not one telescope, but it's actually made up of more than 60 different dishes that are located in Chile, and they can move them around to create an effective diameter of over 16 kilometers. These are used to look at really long wavelengths of light. Like I mentioned with resolution, the longer wavelength you want to look at, the larger a diameter you need. With radio telescopes, one thing you can do is actually have multiple telescopes and effectively build a larger telescope out of many smaller ones. This is done at ALMA, and it's also done at the Very Large Array in New Mexico. I think they're really fun to look at. The important takeaways here is that telescopes are giant projects involving a ton of really complicated engineering, and they come in all sorts of shapes and sizes depending on what you want to do with them. I hope that today helped you understand a little bit more about light and how astronomers use it, how telescopes work, all of that fun stuff. Next week, we're going to come back into our solar system and talk a bit about orbital dynamics and how everything moves in this solar system that we live in. Please like, subscribe, share, ring the bell, all of that YouTube stuff to follow along as we continue our Astronomy 101 lessons.